The direction from which equilibrium is achieved, whether you start with all products or all reactants, doesn't matter. It is only a convention that we calculate K by dividing the concentration of products over reactants, since the reaction proceeds both ways. So, unless specified, read the equation left to right, where left are the reactants and right are the products. This convention makes it easier to understand the meaning of KEQ. The equilibrium constant for a reaction is specific to how the reaction is written. If a reaction is reversed, the new K value will be the inverse of the original value. So for the reaction shown first, where calcium carbonate dissolves into its ions, the equilibrium constant, KEQ, is 6 times 10 to the minus 9. That's much less than 1, and so that means the reactants, or the left side of the reaction, is favored. If I reverse it so that I have the aqueous ions first, 1 over 6 times 10 to the power of minus 9 is equal to 2 times 10 to the power of 8, which is much, much larger than 1, showing that the right side of the reaction, or again, the calcium carbonate, is favored. This does make intuitive sense. If a reaction is favored in one direction, it won't be favored in the reverse reaction. Likewise, if the coefficients of a reaction are changed, the exponents of each substance will change in the expression, thereby exponentially changing K. So if I divide the entire reaction by 1/2, then the equilibrium constant also changes by an exponent factor of 1/2, right? Because coefficients raise our concentrations to their power, so everything raised to the power of 1/2. So instead of 6 times 10 to the minus 9, I have 6 times 10 to the minus 9 to the 1/2 power, or the square root, which is 8 times 10 to the minus 5. If reactions are added together, so I have a multi-step reaction, the equilibrium constants are multiplied. Many reactions occur as a series of steps, so let's consider the production of AgNH3 with a +1 charge. Step 1 is the separating of the silver chloride solid into its ions. The equilibrium constant there is 1.8 times 10 to the minus 10th. And step 2 is the silver ion combining with the NH3 aqueous in solution to produce our AgNH3 +1 in solution. And Kf there, that's just the constant for the forward reaction here, 1.6 times 10 to the 8th. And so if I combine those two together, I get my overall reaction, which I've added there. So you see my overall reactants, my overall products. I just got rid of the silver ion because it appears on both sides. So my net reaction, silver chloride plus 2NH3 to produce AgNH3 and Cl-. And the net equilibrium constant, again, is just the product of those two. And we get 0.028.